All right, let's dive into one of the biggest, most profound mysteries in all of science. We're talking about a force that's pushing our entire universe apart, and it's doing it faster and faster every second. The craziest part? We have almost no idea what it is. So, to get started, let's just ask a simple question. Look around you. Everything you can see, everything you can touch, all the stars and galaxies we've ever observed, all of that makes up just a tiny sliver of reality. So what is the other 95% of our universe actually made of? The short answer is, we don't really know. You see, the first clue in this cosmic detective story came from a discovery that was just absolutely shocking. For decades, we all figured that the expansion of the universe, the one that started with the Big Bang, had to be slowing down. I mean, gravity pulls things together, right? But it turns out the exact opposite is happening. So for the first few billion years, gravity was winning this cosmic tug-of-war. Just like everyone expected, it was pulling everything together and putting the brakes on that expansion. But then, sometime in the universe's history, some mysterious anti-gravity force just took over, and it started pushing everything apart faster and faster and faster. This acceleration is a huge puzzle. I mean, what could possibly be strong enough to overpower the gravity of the entire cosmos? To figure that out, we first need to do a little accounting. We need to take an inventory of everything in the universe, all the matter and all the energy. And when we do that cosmic inventory, the results are just staggering. The normal stuff, the matter that makes up you, me, the planets, the stars, that's less than 5% of everything. The rest is, it's dark. About 27% is dark matter, which is a whole other mystery. But look at that biggest slice of the pie, a whopping 68%. That is the very thing we're looking for, dark energy. Just let that sink in for a second. A staggering 95% of our cosmos is made of stuff we can't see or touch or detect directly. It's humbling. Welcome to the dark universe. And the biggest player in this entire game is that mysterious force causing the acceleration. So let's formally meet our prime suspect, dark energy. It's not just some small factor. It is the single largest component of the universe, and it's the thing responsible for that cosmic speed-up we've been observing. In the standard model of cosmology, we give it the Greek letter lambda, and we define it pretty simply as whatever unknown form of energy is causing the universe to expand faster and faster. Right now, the leading theory is that it's the energy that's just inherent to empty space itself, the energy of nothing, also known as vacuum energy. So how does it work? Well, it's pretty simple, actually. It's the exact opposite of gravity. Gravity pulls everything together. Dark energy pushes everything apart. It's a repulsive force that's actively shoving galaxies away from each other and literally stretching the fabric of space-time. And this isn't some weird cloud of energy floating out there in the void. No, the idea is that this energy is an intrinsic property of space itself. So the more space you have, the more of this energy you get. And as the universe expands, it creates more space, which then creates more dark energy, which then causes even faster expansion. It's a runaway process. But hold on, how can energy push things? This is where it gets really weird, thanks to Einstein's theory of general relativity. It turns out energy can have this bizarre property called negative pressure. Think of it this way. The pressure in a balloon pushes outward. Negative pressure is kind of the opposite. It pulls inward on itself. And through the weirdness of general relativity, that action paradoxically makes space-time expand. It's a mind-bending concept for sure, but it's the mathematical engine that drives the whole thing. So to put it bluntly, we have a name for it, we can see what it's doing, but we fundamentally do not know what it is. As this quote says, it's not just some minor detail we're missing. It's arguably the biggest hole in our entire understanding of physics today. The fact that this repulsive force is dominating our universe has some pretty profound implications for the future of everything. If dark energy keeps pushing everything apart, where does that leave us? What's the endgame? Well, the process is slow, but it's relentless. Galaxies will keep speeding away from us until, one by one, they zip over our cosmic horizon and vanish from view. Our night sky will become dark and incredibly empty. Over unimaginable stretches of time, the stars will burn out, matter itself might decay, and the whole universe will just cool down, approaching a final state of absolute zero.
It's a cold, dark, and lifeless end we call the Big Freeze.
Okay, so we have a culprit for the acceleration, and we have a pretty good idea of the consequences. Case closed, right? Not even close. In fact, our solution, this thing we call dark energy, creates even bigger problems that shake the absolute foundations of physics.
So here's crisis number one. We have this incredibly successful theory of the very small called quantum field theory. It's amazing. And using it, we can actually predict the amount of this vacuum energy that should exist. The problem? The prediction is catastrophically, wildly, epically wrong. The theory predicts an amount of energy that is just astronomically larger than the tiny little bit we actually observe.
How wrong are we talking? By a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It's a number so mind-bogglingly huge, you can't even comprehend it. This isn't just a small rounding error. This has been called the single worst theoretical prediction in the entire history of physics. It tells us something is fundamentally, terrifyingly wrong in how we connect our theories of the big and the small.
And that's not the only headache. We've got two completely different gold standard ways to measure how fast the universe is expanding. One method looks at the light from the very early universe, right after the Big Bang. The other looks at exploding stars, or supernovae, in the universe today. Now, if our model of the universe is correct, these two methods should give us the exact same number. But they don't. And the disagreement, which we call the Hubble tension, keeps getting bigger. It's another huge crack in our standard model.
So what does all of this mean? It means our standard model of cosmology, the lambda CDM model that we've relied on for decades, might be incomplete, or maybe even just wrong. Maybe dark energy isn't some constant, unchanging thing. Maybe it evolves over time, an idea that's explored in alternative theories like quintessence. Really, what these problems are giant clues, pointing us toward a whole new revolution in physics. And all of this leaves us with the final, absolutely tantalizing question. Is this mysterious force that dominates our cosmos a permanent feature of spacetime? Something that's destined to drive us all into that cold, dark future? Or is it something else entirely? A kind of phantom that could change, evolve, or maybe, just maybe, one day disappear? The search for that answer is what makes this one of the most thrilling frontiers in all of science.